Hi, this is another video of the series of videos that explain subwoofer system design techniques. In this one, we will focus in understanding the difference between a physical arc of subwoofers in front of the stage and an electronic straight line that, by the use of different values of electronic delay, will simulate the electronic arc. The very first part is that we will explaining that when we have a straight line or an arc line, the lateral distance between subwoofers side to side, it's important, otherwise we will have a lateral summation. And the reason for doing lines is that what we want to do is to focus the sound where the audience is, and we want to have a lot of attenuation outside the audience. So if we don't pay attention to the separation between the individual subwoofers, we will have lateral summation. The second part that we will explain is about something called window functions, or also called tapering functions, which intention is to smooth the side lobes in the edge of the directivity of the system. However, we will see that the use of window functions will have consequences in the intended sound pressure level, and it is your final decision if you want to use window functions or not. Then we will understand what is the difference between the real position of the subwoofer versus the virtual position that we try to create by the use of electronic delay, and how to calculate the electronic delay as soon as we are doing the design with a physical arc shape in order to do a virtual arc shape with electronic delays. And then we can compare the differences doing physical arc versus electronic arc. For the part of the system design, we will use a calculator made by Merline Van Veen. You can see here the calculator is called Subwoofer Array Designer SAT, and this is the link for the calculator. Also in the description of the video you will see the link. Okay, so let's start, and for the begin, we'll start to continue using Map3D, the simulation predictive software that will help us to clarify all these abstractions. Remember that we have 4 views. The top view is the isometric. The second view to the right of the top is the plan view, or like the drum view. The bottom in the left is like the front view, like if we are in front of the system. And the bottom right is the lateral view or section view, like if we are from one side. Okay, so I will select a system that consists in 8 speakers, and in this speaker, every one of the speakers is being apart by other speaker by 2.5 meters. Something that you may remember from the other video is that this approximate half cycle of the wavelength of the frequency that we are playing, that in this case is 63 Hertz. And also it's important to remember that if I select 2 speakers, but now the distance is twice, in this case I will not select every 2.5 meters, but every 5 meters, what we will see is lateral summation. This lateral summation is because right now, for this frequency, the distance between the speaker is 360 degrees. You may remember that in the page 35 of Acoustical Engineering book by Harry Olson, which was published in 1947, explain this. And basically, let me flip this lateral. So this is the pattern that we are watching right now. This explains that we have 2 sound sources apart by 1 wavelength. It's exactly this. The only difference is that Harry Olson chose half of this simulation. In other words, Harry Olson chose only this part. However, we are intending to see what's going on in the front and in the side. And this one is the pattern when we are half of the wavelength, as the separation, in this case, it is, if we do by half of the distance between the speakers. And now, but it should be in the correct frequency, 63 Hertz. Okay, so this is what has been explained. But now, part of the intention when we are doing our directional system is to avoid this lateral summation. In other words, we don't want by any means that we have sound in this direction. In order to understand this principle, then it's the moment that we need to understand phase mechanism. And in the phase mechanism, in case that you are not aware of this, basically phase mechanism works like a circle, and in this case we will use the philosophy of a watch, where we have the top of the watch in the top of this graphic, and then where around we have the 3 o'clock, this will be 90 degree, and where we have like 6 o'clock is 180 degree, 9 o'clock 270 degree. And if we come back to the top, this 360 degree is like we progress one day, or sorry, 1 hour if we are thinking about the minutes, or 12 hours if we think about the hours. Okay, the important thing about the phase is that if we have sound signals, identical signals with identical level and not phase difference, no phase difference means no time difference or not trajectory by position difference, we will have 6 decibel summation. However, if we start to have phase offset, then we can have 90 degree, that will make that the summation instead of be 6 is 3 decibels. We have more phase shift, 120 degree, we will have 0 decibel summation. 160 degree is 6 decibels of attenuation, and 180 degree, that is half of the wavelength or half of the time period, is 180 degree. A lot of cancellation that can be electrically around 100, acoustically is around 40 decibels maybe, or 30 decibels. Then if we have more phase shift, 210 degree, it's still attenuation, minus 6, more than that, 240 degree, that is 2/3 of a cycle, the level is back to 0. So this means the same as having only one source, and as soon as we have more phase shift, we will get again the maximum summation, that is 6 decibels. In order to make this a little bit more clear, let me use the approach of an oscilloscope. In this calculator that uses the graphication of oscilloscope, what we see is the positive amplitude and the negative amplitude in the vertical, and the horizontal in this case is degree. So we have 2 individual sine waves. Let me do a little bit of offset here so you can see. We have a sound wave blue color, and the peak value is 1, positive and negative, and a second signal red color that right now is being shifted to the right, in other words, being delayed by 10 degree, and the peak value is still 1. What we see in the bottom is the summation of the 2 signals. In this case, the summation of the 2 signals is almost 6 decibels. It's 5.99 decibels, that in linear is 1.99. In this case, we can think that we are talking about volts. So if I go back to 0 degree, with 0 degree, individually in the peak to peak, we can see that the summation is 2 volts in the peak and in the other peak. And this means that the summation in linear is 2 and in logarithmic is 6 decibels. If I go to 90 degree, you can see that now this signal, the red color, is being shifted to the right 90 degree. So this means an electronic delay that causes 90 degree for this signal. Individually, they have the same values peak, but the summation is not anymore 2. Now the summation is 1.41, and this 1.41 represents 3 decibels. If we do 120 degree, means more phase shift here. The individual signals stays with the same level. However, the summation in the peak, you can see that it's only 1. So this means that the summation of the 2 signals is identical level, as individual signal as if we only play one. If I have more phase shift, in this case 151 degree, with 151 degree phase shift, then we have half of the individual level, that in this case instead of 1 we have 0.5, and in decibel it is -6. And then if we have 180 degree is where we have the maximum attenuation, that in this case we obtain 0 volts, and 0 volts mathematically is -infinity, but in an Excel calculator you cannot do -infinity because it shows an error message. So I am doing some condition that in case of that situation indicate -100 decibel. What is important here is that after 180 degree we can have more, so in this case 210 degree more phase offset we are having. Now the two signals summation goes back to 0.5, that represent -6 decibel. Oh, my mistake, is 209. With 209 we have 6 decibels. Then with 240 we go back to 0 decibels. So this means the level of the two sources together plays as only one signal. And if we go more than 240, let's say 300, you can see that now we are having more summation, like in this case 4.77, and when we reach 360, now we have maximum summation. How this can be understood here? Okay, let me tell you. In this case, these two speakers are apart by 180 degree in this frequency. So then lateral, we are in 180. But what happens if I decrease the frequency? Lateral is less than 180, so you can see that the level of the attenuation decrease. And if I go lower in frequency, the level of the attenuation in the lateral decrease, and even lower in frequency, the level of the attenuation in the lateral decrease. It's very important to point that in the front is no difference if we are in the center. So in the front, the distance is not affecting the phase relationship because the two speakers travel the same distance time. What we are discussing is about the lateral. But what happens if I play now this frequency? You start to see that we are having, from the full darkness, start to have a recovery. This is because we are having more than 240 degree, sorry, more than 180 degree of phase shift. And we are going from the 180 in the direction to 360. We are right now approximately in 240. Now we are around 270 degree. You can see that this goes more bright in color. This means more level. If I go to the previous frequency, still, no, sorry, this is the central frequency. This is more than 280. This is close to 140. So this is the reason that the level it's not so intense. Now we should have surely around 270 or 300. And when we reach 360 degree, we can see maximum summation in the lateral. So the intention for doing lines that will not have more than a specific distance is to avoid the lateral summation. And in this case, something important to understand is this. If I go and measure only one of the speakers in the microphone that is in the front, okay, then a single speaker is having the next frequency response. Oh, sorry. This is the frequency response. You can see here that goes from around 30 something hertz to around 100 something hertz. That is the frequency response of this speaker. So it's important to know that the distance between speakers will produce that we can have summation inside the bandwidth lateral. So let me select the lateral microphone and let me select this speaker. But now let me select this speaker. So we have two lateral speakers, but the distance is so large that we will have in the lateral microphone, this is the lateral microphone, a summation at 63 hertz. If I measure only one of the speakers, and I store, says only one. As soon as we play two of these speakers, that can be the number 1 versus the number 3. So this is this distance with full cycle of around 63 Hz. Because of this, you can see that in 63 Hz, the level increases 6 decibels. So you can read the values there. And also we can see that we have this portion is cancel, and this is the next cancel. So this is basically lateral comb filter. But if we select two lateral speakers side to side, in this case will be the number 1 and the number 2, now you can see this lateral cancel. And important to understand, in the comb filter, at twice the frequency that is around here, we have 6 decibels more than an individual speaker. However, in this case, this is outside the bandwidth, so this is beyond the low pass filter. So the trick here is this, that the distance between lateral speakers should never reach 360 degrees. The distance between lateral speakers, my mistake, it should never cross 240 degrees, because in this case you will never have lateral summation. And it's something that can be understood here, but also if I do here 240, that will not allow more than the level of a single speaker. So in this case, if we play all speakers together, let's say in 63 Hz, you can see that this is no lateral sound. And if I do in lower frequency, still no lateral sound. If I go lower in frequency, no lateral sound, even lower in frequency, no lateral sound. But what happens if I am in the 240 degree frequency according to this space? Then this is the level as only one speaker. So this means that laterally they are not increasing for this frequency. But what happens if I go higher? If I go higher, you start to see summation. This is the lateral summation. And if go around one cycle of separation is where you can see the lateral summation. So one of the principles for doing lines is to avoid this lateral summation. In this case will not be a big problem because this frequency is after the low pass filter. So if I select a microphone that is the lateral microphone, this is the lateral microphone, you can see that in the lateral microphone, this is the portion of frequencies that are trying to have summation and is outside the lateral frequency. So let me do this. It's outside the low pass frequency. So in other words, let me do lateral, store here, and this lateral is at 30 meters from the center. So let me put a microphone 30 meters from the center but in front. So then you can see what is the difference between being in the front and being lateral. And here in the lateral, this is where it's trying to have summation, but it's after the low pass. So the trick then is that you know what is your low pass frequency, and what you will do for your maximum separation is 2/3 of the wavelength of the low pass frequency. That was explained in a previous video. Okay, so now let me go back to 63 and we don't need this anymore. Okay, let's start to understand something that is called window functions. And the window functions, that is also maybe called tapered functions, are mathematical equations that will try to smooth the side lobes. And basically what it's doing is having proportional attenuation, gain attenuation, from the central speakers to the lateral speakers. The more offset to the center, you will have more attenuation. The proportion of the attenuation from the center to the outer is basically the mathematical equation, and this mathematical equation is what is called as the window function, and these are the same mathematical equations that are used in FFT analyzers. You may be familiar, if you have used analyzers, with any one of these names that are names of different window functions, from Lanczos and Tukey, that are the oldest one being created, to the newest ones that can be the Blackman-Harris or the HFT 2236D or Kaiser. Okay. Other important thing with window functions is that they will have effect in the sound pressure level in the inside the coverage area. So what we will do now is start to go to understand window functions. So for understand window functions, I will use this calculator, the calculator Subwoofer Array Designer made by Merlin, and let me have speakers that will have 2.5 meter separation. Let's have 8. So we have 8 speakers separation. We have a physical array. The speakers are these black dots, and we have microphones that go from the center to the in front of the last of the speakers. These are frequency responses of these speakers in any one of these microphones. Okay, so, and this is a straight line. It is still not an arc shape, like if I do here 45, then you can see a 45-degree section of a circumference, and that will change the individual level per microphone position, and it will change the directivity front and back. But let's start with 0 degree. And now let me do this, because around here I want to see a little bit more of the prediction of colors. But now let me go here and explain you that this area here in the bottom is called window functions. And it's important that we pay attention with window functions that what will happen simultaneously in several parts of this calculator. One of the parts will be from speaker number 1 to speaker number 8 in the level. The speaker 4 and 5 is the central ones, and the 1 and 8 is the lateral ones. So pay attention to the level here. Then, what is the other thing that we have to pay attention? The level per microphone. So the red color microphone is the loudest one, and we need that you pay attention to the level of the loudest one as soon as we apply taper. Okay, you can see here the names of the different window functions that Merlin has included in this calculator. Okay, so this guy goes here a little bit smaller. Okay, and let's have this guy here. We just need to see from the number 5. Okay, 5, 6, 7, 8, because 1, 2, 3, 4 are identical as 5.78. Okay, so the name of the window function that Merlin is including, you can see no window, that is also called rectangular, and then you have Bartlett, Bartlett-Ham, Blackman, Blackman-Harris, Blackman-Alcosire, Flatto, Gaussian, Hamming. This one that is called Hanning, in reality is Han, as you can see here, Han, then Lanczos, Nuttall, Tukey, Kaiser, and one that surely is a creation of Merlin, that is a logarithmic attenuation in a step from the center to the outer in this quantity of decibels. Okay, so what happens, and look, this is the other thing that you have to look for. Pay attention to this, what is kind of petals, this kind of lateral attenuated level. And what happens if we do window function Bartlett, that is the number 2. Now looks more beautiful, and you can see the relative attenuation from the centers to the outers. And the attenuation is it's in a way that the outer speakers are being attenuated 12 decibels, the next one going to the center 6 decibels, the next one to the center 2.5, and then 0. So what happens if you attenuate the speakers? Well, the benefit that we can see here is that the side lobes are being attenuated dramatically. However, the SPL inside the coverage area also attenuate dramatically. Look at this. Let me go back to no window and the level goes up. Let me go back to the Bartlett and the level drops. The attenuation or the loss of power that we are having in the coverage area is indicated here. 4.08 decibels is the price to pay to make the graphic more beautiful in the prediction software. So this will be your decision if you want to have a more beautiful graphic or you want to have more power in the real world. Okay, so go back to the original, and now let me do Bartlett hand, that is the number 3, and Bartlett hand looks like this. What is the difference between Bartlett hand and Bartlett? Okay, the difference is small, so what I will do, and you can see that Bartlett hand, the attenuation in the laterals is 16 decibels. Remember that before we used to have 2.5, 6, 12, now 2.29, 7, and 16. I will go to Blackman, that is the next one, and with Blackman the level drops more dramatically. And the attenuation in the outers is 25 decibels, oh my god, and the graphic looks amazingly beautiful. So again, if you are fancy for beautiful graphics, window functions. But this is because you are not interested in having SPL, and in this case with the Blackman, you are missing 6 decibels of power in the total level in the audience area. Let me do number 5, Blackman Harris. Blackman Harris, it's open a little bit more, and the attenuation in the outer, you can see 35 decibels. Then Blackman Nuttall. Blackman Nuttall, okay, the attenuation in the outside, it is 7.17 decibels, so you can see the attenuation here is pretty impressive. Then the number 7 is cosine function. Cosine function has a different shape in what you observe, and in the cosine, the attenuation in the sides is less, so this means the total drop of power in the audience area is less. In cosine is only 2.86. Then the flat top is having this shape, and in order to save time, I just will go showing one by one. Number 9 is Gaussian. Number 10 is Hamming. Number 11 is Han. Number 12 is Lanxos. Number 13, Nuttall. And I want to make you bring your attention that these 14 and 15, these guys are having very small drop of power, but you will see why. Okay, so let me do 14, that is the Tukey. And in the Tukey, you can see the side lobes, but the attenuation to the sides is less dramatic, and you can see the drop of power, it's only 1.46. If we compare no window function versus Tukey, you can see that the side lobes are being attenuated, that is being shrink. And what happens if I go to the 15, that is Kaiser? In the Kaiser, well, we can see side lobes, but not as large as with no window function, and the attenuation is the smallest possible. It's only 0.79 decibels, and the reason for that is that the lateral attenuation to the sides, it's only 2 decibels in the outer ones. And now I will go to the number 16. So what you will see that the steps of attenuation goes in 1 dB, 1, 2, 3, and this level of attenuation 3 is the level that you establish here. Okay, so then, as I say before, this will be your decision if you are from the team more power with the audience, or from the from the team more beautiful graphic. Is your decision. Well, this is the thing about the window functions that normally for most of the people it's a mystery. What's going on with the window functions applied to the arrays? Okay, so now let's jump to the next topic. And the next topic, after understanding these window functions, if I go back here, is that understand the difference between a real displacement and a virtual displacement by electronic delay. What I mean with displacement, okay, let me select only this view and let me do zoom in here and pay attention to these two central speakers. So I will select these two central speakers, and the distance between these two speakers is making that lateral we have attenuation. Okay, so because this attenuation, what we will see is that we have cancels pointing to where the speakers are, and we have summation in the front and summation in the back. Okay, but what happens if instead of doing this, we do an arc shape? In this case, now we have the speakers, but the speakers are adjusted in this shape. So this means that the summation will go here in the front, and the summation will be here in the back, and the attenuation will go in this direction and in this direction. So what I will select only these two guys. Oh, I am not selecting the guys. Now I will select only these two guys and check what is the result. So you can see that the energy in the front and back is shift, and the direction of the cancels also is shift. Let me correct my arrows that I can see that they have a little bit of error. So this is the direction of summation in the front, summation in the back, and the cancel come from here and the cancel come from here. Okay, this is physical position. But now the important thing to understand is that instead of doing the physical position where the second speaker, as we can see from the position 0, is being displayed to the back 42 centimeters, what we will do is replace 42 centimeters back by doing electronic delay. So this means that now this speaker is not being shifted back, it's in the position 0, but the electronic delay for this speaker that is 60 degree to L, in the processor 60 degree BL is this, it's 1.1 milliseconds. So the 1.1 milliseconds is what we are using to replace the fact that before it was being shifted here back. Then, as soon as I will play the prediction, you will see that it will not work in this way anymore. What will happen is that the back will be an image from the front. So this means that will go in this direction. And the cancel area in the back will not come from here, but will try to come from here. But we will see that this will not be the same in every side, and I will explain in a moment. So select only this guy and predict. Okay, so you can see here that this is not anymore, and this is not coming here anymore, it's completely straight, and you can see that you have two straights here. So this is not anymore, it's going this way, and it's going from these two ways and going this way. And if you are confused, well, I have to tell you that I have been there before in my life many years ago, but it didn't take so many centuries for me to understand what happens. Okay, and let's explain what happens. If we have a physical displacement, let me draw an X here. This is one speaker, an X here. This is the second speaker. So if I remove the speakers from the visualization, so you have one speaker closer to this 0 line and one speaker that is close more behind. So what happens when we do the electronic delay is that the speaker is not anymore here. The speaker is in the original position, so this means that it's here. And what the electronics delay is doing? Well, this is the typical misconception from people that electronic delay is moving the speaker with the electronic delay back. So people say, yes, the speaker is moved back. No, my friends, the speaker is in the same position. The electronic delay, it's also affecting from the rear. In other words, a person that is in the rear, the electronic delay will move the speaker far away from him, because the electronic delay is not other thing than additional latency. So the way it works is this. If we have electronic delay in this speaker, then when we send audio signal, the first speaker will start to produce waves. And at some point, the second speaker start to produce waves, and the difference in this position to this position, this position to this position, the perpendicular line is the guideline for where we are focusing the sound in the front or in the rear. Sorry, the front in physical position. But what happens with electronic delay? With electronic delay, what happens is that, remember that the sound in these speakers goes in all directions. So this means that in the same way that travel to the front, travel to the back, travel to the one side, and travel to the other side. We can understand this as circles. So let me draw here like a circle. And let's say that the electronic delay of the other speaker, this speaker, is being adjusted in a way that when the sound of this speaker travel this distance in all directions, then this speaker start to produce sound. When this speaker start to produce sound, then the intersection of this line to this line is the same in the back. So this is what will make that in this direction you will have sound here, and in this direction you will have sound here. So this will be like a mirror image. It will be not like the opposite. Then electronic delay and physical displacement is not the same. So I will show you again these two guys with physical displacement. Oh, it's better that I just recall the plan view. No, plan, and actually let's view all together. Okay, let's do only the from the center to the next one, and you can see here how the sound goes. So we can set markers here in this 3D, one here and one here. But now let's do the electronic delays, the same speakers. And you can see that now is different. In this case, the back goes in this direction. And it's important to understand this, because as soon as we compare the full system, what happens in the back with electronic delay is not what happens in the back when we have a physical arc shape. So I was close to forget something additional, that is this. If I check in the next page from the Harry Olson book, next page from 35, we have straight line sources. This one, as has been explained in the previous presentation, it is the one that defines the directivity that connect how long is the array versus the wavelength for every given frequency, that will make that, in understanding the directivity of a full straight array. Basically, we can consider that from being in front of one H speaker to being in front of the other H speaker is where we will have the directivity. So the sound is inside this rectangle, and outside this is where we'll have the attenuation. Okay, so something that I have to say is that if I progress few pages, in this case to the page 40, you can see curved line source or arc. This is the one where Mr. Harry Olson described the curved shape and the directivity of array systems that are arc shape. And by the way, the one that explained how to use this by electronic delay, it is here in the same page 36. It's called beam tilting by phase shifting, that he explained that we need to use different delay values from the center, zero delay, to more delay in the outers to produce this deviation. So in other words, this is not new technology or modern design techniques. This is very, very ancient techniques. Okay, having said this, let's go back to understand how to calculate the electronic delay that will replace the physical displacement by the value of electronic delay in your processor. Okay, this displacement is very simple. I can see two letter P. This displacement is very simple. The time in milliseconds is the displacement. In this case, I will use metric in meters, divide of the speed of sound, again in meter per second. And in other words, time in milliseconds is the displacement in meters divided by what we can say standard speed of sound, 340 meters per second. So if we want to understand this, let me say that in this calculator, subwoofer redesigner, if I say I want to do 45-degree arc shape, the displacement that goes from the center to the outer is what you see here. The centers are the minimum value, 0.04 meter 4 centimeters, and then you can see 31 centimeters, 87 centimeters, 1.7 meters. So if I do this calculator, 1.7 divided by 340, remember that the value depends in the temperature. You can see that Merline here indicate at 14 degrees is 340. Then we have, and I forgot that I have to multiply by 1000. Okay, because we want it in milliseconds. So this is approximately 5 milliseconds. So if I change here to the option number 2, in the option number 2, now the speakers go back to straight, but you can see that the value reached 4.93. That is very close to 5 milliseconds. The only reason that is not 5 milliseconds is because the central speaker is already offset by 4 centimeters. So this means that this in reality is not 1.7, it's 1.76. That is the difference to my calculation. Okay, so you can see the calculator of Merline basically is transforming the original curvature of the arc shape in a physical straight line where from the center to the outers you will have more electronic delay. And of course, if your display angle, if your arc shape is a smaller arc, in this case is 20-degree arc, your delays from the center to the outer is not as large. Look at this, the outer is 2.2 milliseconds. If I do a larger arc, now the focal point is closer. Now it's 4.39 milliseconds in the outer. And if I do even larger arc, so the focal point is even closer, now we have 6.55 milliseconds. So this is the way for doing this calculation. Now you don't have to worry because this calculator can do for you not only this calculator, there are many calculators, and surely you are capable for doing a calculator also. So now the other important thing is that if I have here arc shape, you can see that the arc shape is wider directivity in the front. And remember that the directivity in the front, basically, it is defined by, let me change here to do the option that will have the array, okay, that will deploy the microphones from the center position on axis to the intersection from the focal point to the last speaker. This is the microphone. So when we see this, we can see the difference in level with microphones. And if you remember from the other video, 67% from the on-axis to the outside that intersect the last one is where you will cross more than 6 decibels of attenuation. That is basically here the microphone 6 and microphone 7. So microphone 6 and 7 are showing more than 6 decibels. So in other words, the usable area in this case is not 60 degree, but 2/3 of 60 degree that in reality is 40 degree. This is the usable area if you don't want to cross the -6 decibels. In this calculator, it's indicated here, where you can read max angle, 40 degree. This is the maximal usable angle that I can hide, the one that I don't want. So the variations inside the on-axis to going outside the system, it's in 40 degree. This means 20 degree from one side and 20 degree to the other side. Important thing is that in the focal point, all the speakers arrive at the same time, and because of that is where you will have the maximum summation. But when you do electronic delays, the rear will be same directivity as in the front. So why? Because as we explained before, electronic delay is not moving the system, but is adding more latency. And the other important thing, remember that in this cell, red color, 136, this explains where you will have lateral summation. So if I play 136, you can see the lateral summation, and if I go to a system with arc, and if I remove the arc shape, you can see very clear the lateral summation. Of course that if the lateral summation, it is outside the crossover point, it's not a problem. So in other words, if I put the microphone from 0 to the 90 degree of axis, the lateral summation that it is the microphone black color, it's here, and it's outside the low pass filter. So this means that in the reality, the maximum frequency that I will play is 90 Hertz, so this will not be lateral summation. So if we try to compare here, then the 20 degree system arc shape we have here, you can see wider in the front, narrow in the back. And if we want to compare with electronic delays, you can see that with the electronic delays, the only thing that is happening is that the speakers are being from the arc position to the front. So let me take this guy out, come back here all together, and now you will see that it's wide in the front and it's wide in the back. If you want more wide in front, you need to have an arc shape that has shorter distance radius, then you have wider directivity and you have narrow directivity here in the back. However, if we do the physical straight line with electronic delays, the directivity in the front and in the back, it is similar. And if you want wide more, like 60 degree arc, well, you can see very wide directivity. And now the focal point is here, is where you have the maximum summation behind. However, if you do the 60 degree with electronic delay, then you will have wide in the front and wide in the rear. Well, this is the intention of this presentation, that if I come back here, we are seeing the difference between doing physical arc shapes versus electronic delays to simulate the arc shape. They are not exactly identical in the back, but they are identical in the front. Well, I can tell you that this is the end, and there will be more presentation in subwoofer designs. So thank you very much for your attention.